Hello, everyone. I'm Avi Kivity. I'm the CTO of ScyllaDB. In this talk, I will describe what we've been working on for the past year and the things that we're preparing for the following years. I'll be focusing on ScyllaDB core. Quite a lot of the action is happening outside the core with serverless and with drivers, but I will leave that to others and just talk about the core database. So let's start. Here is the agenda, the list of things we'll talk about. I won't read you the slide. Let's get started. So first, we've enabled the repair-based node operations. Now that's a little bit of a mouthful. So what are node operations? Those are all operations that deal with topology, with changing how data is laid out across nodes. Adding nodes and removing nodes and rebuilding nodes that have had faults. And what we've done is we made all node operations be based on repair. And that allowed us to consolidate some code and add a lot of properties to those operations. So bootstrap and decommission become resumable. And when we stream data from one node to another, we can stream from the primary replica, which was the case before we had the repair-based node operations. But we can also stream from a quorum of replicas if the primary is missing. And that allows us to perform node operations in the face of faults. And as a result, we have better resilience, better fault tolerance, and correctness is also better. Another thing that we've worked on is automatically parallelized queries. So the majority of queries in ScyllaDB only have a limited amount of parallelism. So for example, if you read a partition, then the query will go to a particular node and a particular shard within a node. So they will not be distributed across the entire cluster. Within the node, there will be some parallelism as you read from multiple SS tables in parallel in order to reduce the latency. But otherwise, it's limited to a single node and a single shard, perhaps a quorum. But there is a class of queries that can benefit from parallelization, and that is the aggregation queries that scan over the entire table or maybe a part of a table. And previously, these queries would be done via Spark or perhaps custom code. And of course, you can still do that. But you can also use a simpler route, which is to use a CQL query. And the query optimizer will recognize certain patterns and will automatically dispatch the query first to all nodes within the cluster or all relevant nodes that hold the data, and then each node will dispatch the query to all of the vCPUs within that node, and all of your disks and all of your vCPUs will be working to get the answer as quickly as possible, and that can easily result in 100-fold reduction in query latency. So those are usually analytical queries, not OLTP queries, but still you want the answer sooner rather than later. So this is a nice improvement, and we're looking to increase the scope of this to recognize more and more patterns so more queries can be automatically parallelized. Another feature that works very well with the previous one, with automatically parallelized queries, is user-defined functions and user-defined aggregates using WebAssembly. So in conjunction with parallelized queries, you can distribute the computation across the entire cluster. And instead of pulling data into your compute nodes and then performing a computation in your client, you can push the computation, push just the code that performs the computation into the database and have it run close to the data. So there are no data movement. The data is operated on in place. And because we use WebAssembly, then you can use any language you like. There are some limitations, and right now the limitation is that the language must be Rust, but because it's so popular, I guess no one will mind. We may add more bindings in the future because the infrastructure does allow any language to be used, but right now we focused on Rust. The computations run in a sandbox, which means that they cannot affect other operations on the database node, which is important for safety. And it's also protected in terms of latency. So even if you have a long computation, a long running loop, or you use a lot of memory, it's isolated from other queries and will not impact their latency. And the use case is usually analytics. So if you want to reduce the data in some way that's not provided by the default SQL functions, you can write your own reduction function and push it into the database and have the database perform the computation for you. Another feature that's became available recently is per partition rate limit. And this allows you to have a rate limit imposed on partitions, different rate limits for read and for write. And the primary use case is to prevent bot accounts or runaway APIs from spamming the database and overloading a particular vCPU, which in turn causes a reduction in service level from the entire database. Now, this is possible to do on your own on the client side, but it's often quite difficult because the client side is distributed and it usually has no central point of coordination, or rather its central point of coordination is the database itself. So the natural place to add rate limits on partitions is the database itself, and that's what we've added. The chart at the bottom explains how it works, but it's a little bit too involved. So if you want to understand it deeply, you can watch Piotr's talk about it. This is where I stole that slide from. So I recommend watching that presentation if you're interested in it. Next, we've updated our alternator implementation. Alternator is our implementation of the DynamoDB API. DynamoDB, of course, is the NoSQL database provided by Amazon. And we have a compatible implementation that implements exactly the same API, only it's much less expensive and faster. And one of the features that we had missing was time to live. Now ScyllaDB has time to live in its SQL mode, but it has different semantics, and so we needed to implement time to live for alternator in a different way. So this is what we did. We also improved its performance. Alternator performance lags behind SQL performance, but we're determined to make the performance difference as small as we can, so that you can use alternator without thinking that you're losing performance. We had a bunch of bug fixes and small improvements as well, but I will not go into the details here. Another major topic for us is the consistent schema and topology. So with the current ScyllaDB schema and topology management, the operator has to be very careful not to perform certain errors because the result can be pretty bad. So if you perform concurrent schema changes on the same table, or you perform concurrent topology operations, usually you will be rewarded with a nasty failure mode. And so we've added raft-based coordination to make sure that this doesn't happen. So the first implementation, which is already available in 5.2, does not add new capabilities, but does protect you from mistakes. But of course, we want to gain advantages from, not just protect from errors. And the advantages that you will see from raft topology is that you will be able to bootstrap and decommission nodes concurrently. So this means that you can scale up and scale down much faster than you can right now. We will support tablets, which is a different way of distributing data across the cluster. And with tablets, the data layout is can be different for different tables. With the current strategy, which is called vnodes, data is distributed the same way for all tables, at least all tables within a key space. And this is suboptimal when some tables have a large amount of data and so need to be distributed across a large number of vCPUs and nodes. And you can also have smaller tables which need less distribution. And tablets allow each table to have its own control over how it is laid out across the cluster. And finally, we will be adding a strong consistency mode. Actually, we already have an experimental strong consistency mode, but this is more oriented towards database developers rather than database users. We will be making it available for users as well, for users who want something different than the eventual consistency model. And there is a talk by Kostya that will explain all this in much finer detail and with nicer graphics too. Next, we've revamped our I/O scheduler, and the I/O scheduler now has a much better model of how the disk operates. So in this graph, you can see measurements that we made across a wide variety of workloads. So on the x-axis, we scale the write bandwidth from 0 to 1 gigabyte per second. And on the y-axis, we scale the number of operations, of read operations per second, random read operations per second, from 0 to 200,000 or 250,000 ops per second. So you have a matrix of different workloads. And the color indicates the latency that we measured on those workloads. On the top chart, it's the 50th percentile, the median latency. And on the bottom chart, it's a 95th percentile. And of course, we measured the latency of the read operation because that's what's important for us. And the color indicates the latency. So the lighter the color, the lower the latency. And you can see that in the top right half of the chart, where the color is white, the disk simply isn't able to sustain that workload. And near the boundary, this diagonal line, the latency becomes higher. This garish purple color indicates that the latency is around 5 milliseconds, which is too high. And now the changes that we've made allow the I/O scheduler to know where in this chart the disk is operating and to keep the write bandwidth and the read I/O operations per second in an area where the latency is acceptable. And if it sees that the latency, if we reach an area where the latency is too high, then it will throttle the write bandwidth down in order to keep it acceptable. So we've seen very good results from the I/O scheduler. It's available in ScyllaDB 5.0, and with an improved version is in 5.1, and we will keep fine-tuning it so that you will see the best latencies possible, even under the most demanding workloads. Another area that we've worked on is trying to eliminate all the corner cases. Those corner cases usually affect only 5% or so of the users, and 95% never sees them. But if you're part of that 5%, then it's incredibly annoying because the behavior in those corner cases is usually pretty bad. So let's look at a few examples. So one example is reverse queries. So all ScyllaDB versions supported the reverse queries, and if you had small partitions, a few megabytes or so, they would work perfectly well. And of course, if you didn't use them, they also work perfectly well. But if you are a user that uses reverse queries and you had moderately large partitions or even larger, then they would behave, they would be very slow and consume a lot of memory. So in 4.6, we added reverse queries that were much faster than before, but they could not use the cache. And in 5.0, we made them fast, and we also made them serve from the cache. So they would work well both for small partitions, usually from cache, and for large partition, usually from disk. And they work well with the driver paging. On the right, you can see an example of a SQL query that is reversed. The descending keyword tells the database to read the partition from back to front. Another example of a corner case is handling large runs of tombstones. So I guess most of you are familiar with tombstones in the context of a NoSQL database, but I'll refresh your memory anyway. Tombstones are used to mark deleted data. So instead of finding the data that needs to be deleted and removing it from the disk structure, instead we insert a marker called the tombstone that indicates that the data is removed. And one problem is that you have a delete-intensive workload, then you can get a large number of tombstones in the database, and when you query, the database will read those tombstones and filter them out, so they don't return any results. And one problem that we had is that if you had a large run of tombstones, so a large section of the data that was nothing but tombstones, then the performance would be very low, and in certain cases it might have consumed large amounts of memory, even to the point of running out of memory. And we've fixed that. So usually the recommendations for NoSQL database tell you to avoid performing such workloads with lots of deletes, but real life sometimes requires it, and now ScyllaDB will support this use case well. Another area that we've improved is range tombstones. So range tombstones are deletes that delete a large number of rows at once in a single statement. And previously, if you had many such range tombstones within a partition, then you would experience very bad performance. And we've improved that. We're also working on improving the handling of tombstones within the cache. So the cache is learning to evict tombstones when it can get rid of them, so that it will recover memory and improve performance. Yet another area is out-of-memory handling. And I'll say a few words about why it's needed in the first place. The database has conflicting requirements. On the one hand, it wants to run queries in parallel in order to be able to saturate the disk. And the disks really like having multiple read requests running in parallel in order to extract the best performance. But on the other hand, it has a limited amount of memory, and each query can take wildly different amounts of memory. So a query might require just a few hundred bytes. For example, if it hits cache directly, then it just copies the data from the cache. Or it might require multiple megabytes if you're reading large rows that and you need to merge multiple SS tables in order to construct your result. Then you can have queries that require holding tens of megabytes in memory. And if you multiply tens of megabytes with high concurrency, you're starting to reach a situation where you might run out of memory. So the way to combat that is to have countermeasures that apply as memory usage grows. So when we reach one threshold, we simply prevent new queries from starting. And we've had that for a long time now. It's not new. But a problem is that a query can continue to grow its memory consumption after it started. So even if we prevent new queries from starting, still you can have the existing queries grow in size and consume more and more memory and eventually run out. So we've added another threshold, and when you reach that threshold, you pause all of the queries except one, and in this way they do not consume more memory, and you allow just one query to allocate more memory, and this reduces the rate at which memory is consumed, and eventually that query will complete and return its memory to the system, and things will resolve. But there is a possibility that even that is not enough. So if you reach yet another threshold, then we start canceling queries. So all queries except one query. And this is a kind of emergency measure that allows the system to recover. That query is completed, and then those other queries can be retried. So it's not good when that happens, but it's a lot better than having the database run out of memory and start misbehaving or crashing. Yet another feature is repair-based tombstone garbage collection. Yet another mouthful. So the goal here is to eliminate something called GC grace seconds. And GC grace seconds in the amount of time we keep a tombstone on disk. Usually it's 10 days by default. And the idea here is that you keep the tombstone around in order to assure it gets propagated via repair to all replicas. And this way you don't lose the tombstone. If a tombstone is lost, then you might have data resurrection. Now this has two downsides. One downside is that it might be more than necessary. So if by keeping tombstones for 10 days, you might accumulate a lot of them, and that reduces performance and consumes disk space. And the opposite problem is that it might not be enough. If the tombstone hasn't propagated in 10 days to other replicas, then you might end up with data resurrection, which is bad. So our fix was to tie Tombstone garbage collection to the repair functionality. And this way, if you run repair frequently and repairs complete and everything works, then we can garbage collect those tombstones early as soon as the last repair completes. And if for some reason you did not run repair, maybe there were infrastructure issues, or maybe you do not have the performance bandwidth for that, then it will keep correctness and not garbage collect those tombstones. It does impact performance, but correctness is often more important than performance. Let's take a look at some things that we're preparing. So we're working on morphing the SQL grammar towards its older cousin SQL. So the two dialects are very similar, but still they are different, and that causes some confusion for people who come from SQL. So one improvement is we're relaxing a lot of constraints. So there are a lot of examples where SQL is very limited. So you can write a equals 3, but you cannot write 3 equals a. The grammar will just reject it. And you cannot write a equals b, where a and b are two columns in your table. So one of our goals is to make it easier to write expressions and not have them rejected by the grammar seemingly randomly, unless you're very familiar with the grammar. There are also some places where it's semantically different. So the most annoying example is lightweight transactions if clause, which compares null in a different fashion than the rest of the system. So the lightweight transaction if clause will consider two nulls equal, whereas standard SQL considers them unequal. So that can be surprising, and we'll be working to provide to resolve that and make the semantics coherent. Of course, we'll provide an upgrade path so that we will not break the code of existing users. And we'll be working to make automatically parallel queries recognize more and more patterns to make them more usable. Another topic is object storage. So, of course, storage, there's lots of different kinds of storage available. There is RAM, which is extremely fast, but also extremely expensive. There's NVMe storage, which is very fast, so 100 microsecond response time, but still it's relatively expensive, although it's getting cheaper all the time. And there's hard disk storage, which is very slow, but also very inexpensive. And to add to the mix, there is in cloud environments, there is also object storage. So it's even slower than hard disks. It's usually based on hard disks underneath, but also with a network hop. But on the other hand, it is very cheap, and you can expand it very easily. It's just an API away rather than acquiring a disk and installing it away. And I guess what's most compelling about it is that it's very easy to manipulate. You can easily copy it, easily back it up, and you can access it from different nodes very easily. So it's shared by default. And this leads to scenarios where it's very easy to grow your cluster, since you add new nodes and they already have access to the storage. They don't need to stream the data from one node to the other. So that's a very interesting use case, and we're working on making it available. And we see two use cases for that. One use case is where you have very dense databases that manage very large amounts of data, but with a small number of nodes. And this will work where latency is not very important. And another use case is tiered storage, where you have a mix between NVMe storage and object storage, and you try to mix the latency as well. So you try to get most of the queries responding with low latency, but the bulk of the storage, and therefore the bulk of the cost, will be on the less expensive object storage. So this is a way to try to gain the best of both worlds. And that's it. Thanks, everyone. My contact details are on the slide, so you're welcome to follow me or contact me directly.